We now understand, based on the Clausius-Clapeyron equation, that enthalpy of vaporization is really the key to understanding differences in boiling points between different compounds. The origin of enthalpy of vaporization has to do with the idea that in condensed phases, molecules are attracted to one another through intermolecular forces, and vaporization causes disruption of these intermolecular forces since it causes the molecules to separate. That's why delta H of vaporization is always positive. An input of heat is necessary in order to facilitate this breakage of intermolecular forces, this disruption of intermolecular forces between molecules in a condensed phase. To understand intermolecular forces on a deeper level, though, we need to appreciate how they flow from molecular structure. In this video, we're going to introduce the idea of intermolecular forces and look at some of their general properties. Let's revisit some of our intuitions on enthalpy. Remember, we saw before that breaking bonds requires an input of heat, meaning that delta H is greater than 0 when we break bonds on the molecular level, while forming bonds releases heat, corresponding to a delta H within the system less than 0. That means that a substance with highly negative enthalpy of formation has a large number of bonds, at least relative to the number of bonds in the elemental forms. A good example is illustrated by the hydrocarbons below. As we move to larger and larger hydrocarbons, we're introducing more and more carbon-carbon bonds. And if we pay attention to the delta H of formation values, we see that they increase with the number of carbon-carbon and carbon-hydrogen bonds within each structure. This has to do with the idea that forming bonds releases heat, making the enthalpy of formation more negative for substances containing more bonds. Water is an interesting exception to this idea. If we just look, for example, at a single water molecule, we find only 2 bonds within. So there are a much smaller number of bonds per mole, for example, in water than there are in N-pentane. But the enthalpy of formation of water is crazy negative. It's something like 285 kilojoules per mole. Why does water have such a negative enthalpy of formation even though it contains a relatively small number of covalent bonds? The answer here is that bonds between molecules influence enthalpy as well. Just as enthalpy of formation becomes more negative as we add more covalent bonds, as we add more bonds between molecules, enthalpy of formation also goes down. And the bonds between molecules in water are extremely strong relative to bonds between molecules in something like N-pentane. This directly explains its very negative enthalpy of formation. These bonds between molecules are what we call intermolecular forces, IMFs, or on occasion where we want to ensure that we capture both atoms and molecules, we'll call these interparticle forces, or IPFs, but IMFs is actually the more common term. Intermolecular forces are attractive. They're bonds, really, between 2 different nearby molecules. And the basic idea underlying all intermolecular forces has to do with electrostatic attraction and Coulomb's law. Here it is again. What can happen when 2 molecules are near one another is, for example, a negative region of one molecule can interact with a positive region of another molecule, leading to an attractive force according to Coulomb's law. This can happen between 2 molecules with permanent dipoles, a molecule with a permanent dipole and an ion, or even 2 molecules with only temporary dipoles. And we distinguish the different types of intermolecular forces by the types of charges involved, whether we're talking about full-on ions, covalent molecules containing permanent dipoles, or covalent molecules containing only temporary dipoles. We typically draw these as dotted lines between the interacting portions of adjacent molecules because what we find is these are not as strong as covalent bonds. So we can't, for example, use a solid line to represent an intermolecular force because really the bond is not as strong as a covalent bond between 2 atoms. Importantly, and as is suggested by Coulomb's law actually, intermolecular forces require close proximity between the molecules involved. Only molecules in close proximity can engage in these forces. And so intermolecular forces then are only important, or only really important, for the condensed phases, solids and liquids in which particles are very close to one another. So check out these images of solids and liquids on the microscopic scale. Notice that the atoms or molecules in the substance are very close to one another. They're randomly dispersed in the liquid and they're in a regular lattice in the solid, but in both cases they're definitely close enough to interact through intermolecular forces. In a gas, intermolecular forces become much less important and in many cases essentially non-existent. And this is a key assumption of, for example, the kinetic molecular theory, that the distance between gas molecules is so large that we can essentially ignore intermolecular forces. Because IMFs are strong in the condensed phases and relatively weak in the dispersed gas phase, in going from a liquid to a gas, we have to input energy to overcome the intermolecular forces. That's why delta H is greater than 0 in converting from a liquid to a gas. The enthalpy input that we have to put in is essentially equal to the strength of intermolecular forces in the liquid. A good example is provided by hydrogen bonding in water, and it's these very strong hydrogen bonds that explain the surprising heat of formation of water. What happens in water is that the positive end of one water molecule, which will be near the hydrogen because of the way the bond dipoles work in water, comes into close contact with the negative end of another water molecule, and there's an attractive force here, and there's even a covalent component to this where a partially covalent bond is formed between the positive hydrogen and the negative oxygen. If we understand the nature of water's dipole moment and where its partial charges are located, then we can predict, in fact, that water can engage in hydrogen bonding. And this is what we'd really like to be able to do, to look at the structure of a molecule, its Lewis structure and its three-dimensional structure, its molecular geometry, to predict its dominant intermolecular forces in the condensed phase. It's the dominant force, the strongest force, that's going to dictate the properties of a compound.